It's time for some more Cleo, Abram. Specifically, gravity is fake. Oh, I sure hope not. We rely on gravity a lot in passive nuclear safety systems. For those of you who don't know me, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Let's see what this is all about.
This plane is about to send me into zero gravity for 10 minutes. And I'm going to try to explain why
it's the vomit comet.
Gravity is a lie while I go without it for the very first time.
Gravity.
Gravity ain't real.
Say we don't actually need gravity.
Why is there gravity? Why does it work?
Is this going to be like one of those people that think the Earth is flat sort of deals?
Turns out that gravity is one of the most controversial subjects in all of physics.
This is not some philosophical debate. A huge amount of the tech that you use every day all depend on our current limited understanding of gravity.
Okay.
If we can understand this a little bit better, we can build more things that are huge if true.
So what really is
If true. I know that's her tagline, but that's just funny.
gravity? In this video, we're going deep to learn how it truly works together.
And we're going to do this in 4 levels. Starting
4 levels.
now.
Okay.
Right now, I'm in France, and I'm about to get on that special plane.
Cool.
I've been invited by the European Space Agency as they run experiments for their real upcoming space missions. They do like 2 of these a year. They invite 1 civilian each time. It's a really big honor. I'm also really nervous. It's gonna be great. They call this plane the vomit comet.
Okay, yep.
I'm really hoping that I don't get sick. And as we're getting
I can't say I do the best with motion sickness either, so sure.
ready to take off, I am realizing how little I know about this thing that's been holding me down my whole life. Here's what I
been holding
thought
you
I
back,
knew
huh?
about gravity from high school
been saving
physics.
your life.
We'll call this level 1.
Okay, I think I know what this is getting at. So the whole gravity not being a force thing is quite often misunderstood. That's not level 1, so I'll wait till we get to level 2 or 3 or whichever one that is.
What I learned in school is that gravity is what holds me down on Earth, that it's a force that objects with mass exert on each other. So the Earth pulls me toward it, and I, in some tiny way, pull
it
back
back.
on the Earth too. Same thing
But
with
the
the
Earth's a lot bigger, so yeah.
sun. The sun pulls on the Earth, and the Earth, in some little way, pulls back on the sun too.
And the math that describes this is beautiful. It's just the relationship between the mass of one thing times the mass of the other thing divided by the distance between them squared. And g is a constant. Don't worry about it. So
It's a constant, don't worry about it. It's quite a small constant if you compare it to something like the universal electric constant when calculating electromagnetic forces. But yeah, we're over here in Newtonian physics territory. It's an inverse square relationship, kind of like the inverse square relationship between radiation dose and your distance from the source. You double the distance from the source, dose drops off by a factor of 4. Inverse square law comes up a lot.
this equation tells you how strong that pull will be.
But until today, Earth has always pulled me right down into the ground, which stops me. So to experience the raw, unfiltered effects of Earth's gravity, I need to go into free fall, which is exactly what this plane does. It's gonna rise up and then plummet toward the Earth. This is the part that's making me nervous.
Yeah.
And as it does that, I'm gonna be falling, and the plane is gonna be
Weightlessness,
falling
yeah.
around me. And during that fall, I should feel like I'm floating, like a skydiver or
So yeah, it's a parabolic trajectory that this plane flies at to create the experience of weightlessness, both for the people on it and as well as whatever equipment. This can be used for testing. You could conceivably do something like this to test coolant behavior, because after all, buoyancy goes away when you do something like this, though this is not a very stable situation because it only does it for a few seconds or minutes at a time. Because after all, you can run out of room real quick if you take your plane in free fall for too long. But gravity doesn't actually go away. That's one misconception about this sort of stuff, is gravity doesn't go away. And the acceleration you experience due to gravity, even up at the space station, doesn't go down by very much. You're just orbiting. You're still in free fall. Another word for orbit is a clever way to fall without actually hitting the ground. But that's not what you're doing here. That's what you're doing in the space station.
An astronaut, which is why real astronauts train and run experiments
Yes.
on these planes.
This guy's name is John McFall, and an astronaut. That is hilariously awesome.
But hang on, why is rapidly falling anything like peacefully floating?
Think about it this way. So the Earth's gravity
Well, you're orbiting the Earth, though. Yeah.
creates a pull at 9.8 meters per second squared, or 1g. If you're in a rocket out in space and that rocket is accelerating at exactly 9.8 meters per second squared, you wouldn't be able to tell the difference between standing on the ground and flying in that rocket.
Einstein called this the equivalence principle.
I mean, this is restricted, and it says in a small enough region of space and time, the effects of gravity are indistinguishable from acceleration. You could use the same logic and say you're on an elevator in deep space. Good luck making a space elevator that goes that far.
And honestly, it sounded pretty intuitive to me at first. And then the more I thought about this,
Don't
the
overthink
more
it.
it started to just break my brain. Because if gravity and acceleration are the same, it means that being in freefall without air resistance is the same as floating in space. Because
Yeah, pesky air resistance.
they're both 0g, right?
Yeah, remember this idea. It's going to be important later. But right now,
I don't totally understand this yet. So I'm gonna
Here
go
we go.
try it.
So gravity feels like a force, but it's really curved space-time. And inertial-based navigational systems, such as those used on a nuclear ICBM, must account for gravitational time dilation and acceleration.
Let's do this.
Here it goes.
Okay, so we just pulled up. I'm now feeling increased gravity. You might be able
A
to tell in my
45
face.
degree.
Whoa.
Okay, yeah, you're going to be pulling a little bit of G's. Nothing like you'd experience, say, in a fighter jet, but yeah, you're going to feel heavy.
This feels like being in a car and you're accelerating.
as we shoot up, the acceleration that I'm feeling is about the same
50
as being on a
degrees.
planet with twice Earth's gravity, or 2g.
I'm feeling squished on the floor.
And again, perfectly safe for limited amount of time, especially if you're laying down like that. But can you imagine trying to survive on another planet like that for an extended period of time? Humans would not evolve the way we did.
And then when we hit this point,
Oh my god.
Relief.
Tell us how you feel.
All of my thoughts just left my head. I feel
Of your thoughts. What, did they just float out? That's awesome.
0g.
I've never experienced this, so I don't have a baseline here. You don't have to do something like this to be a nuclear engineer unless you also want to go into space or something.
feels so weird. It's not just your outsides, it's your insides too. So your stomach is moving around and your blood isn't getting pulled down from your head like normal. So you feel like there's more pressure inside of your skull. And then touching
Ooh,
something
that's right.
will move you way farther than you think.
Lay back down.
oh my god. It goes so fast.
Keep your head still.
Okay.
Sit up.
That felt unbelievable. I don't even know what just happened. It's like nothing I've ever experienced before in my life.
Did you enjoy it?
Yeah, I'm not sure you can explain that.
I think so.
I'm not sure.
I'd like to try it again.
Or would you like to get out?
No, I'd like to do it again, please.
We did it again.
Do it again.
1G, 2G, 0G, 2G, 1G, again and again and again.
Loop-de-loop.
To see this happening, just watch what happens when I throw this ball.
This is 2G. I'm about to go into 0G.
Oh, yeah, it's getting heavier. Oh, and there it goes.
This is Einstein's equivalence principle in action. I know that I'm falling in this plane, but I
I feel nothing. I don't feel like I'm falling. I feel like I'm floating. But here's the craziest part. It's not just like I'm floating in space. It is exactly the same thing.
Sure.
Yeah,
I mean,
this
the
is where things
force
start to
balances
get
work
weird.
out.
You will look around and everything will look like it's weightless. In reality, you're inside a plane and you might think to yourself, well, this is some sort of an illusion. What Einstein realized is that situation of you in the plane and that situation of an astronaut deep in space are are equivalent, they're identical. It's not that one looks like the other, but they are the same situation.
If we covered all of the windows, there is nothing that I could do, no test, no experiment, to prove that I'm falling in a plane and not floating in space. This is exactly what Einstein was talking about. And actually, astronauts orbiting Earth aren't really floating. They're falling too.
They're literally falling towards
It's free fall, and orbits do decay over time.
the Earth all the time. And they're just cruising so fast that they miss the horizon and they never crash into the Earth. If you were to stop it from cruising so fast, it would drop like a stone.
Yeah.
Right down to the Earth.
Yeah. And the contrary, if you were to accelerate it, it would go into a higher orbit.
So they are falling all the time. They are experiencing weightlessness all the time.
Okay, fine. So falling is floating. Why does that actually matter? It matters because it means that this plane actually made gravity disappear.
Gravity is gone. It's not there.
How did gravity disappear?
That's a misleading statement, and all right, let's see what they say.
Well, it was never really there to begin
Oh,
with.
here we go.
Yeah, the gravity that you experience on Earth isn't what you think. We're about to enter level 2.
It's not a
but
full- okay.
first,
I've done 6 parabolas, up and down. I'm feeling a little bit nauseous, I gotta be honest.
Just take some time, relax, sit against the wall, chill out.
okay,
Time to
while I
vomit.
do that in the plane, let's talk about level 2. That version of gravity that I learned in school, the masses pulling on each other version, right? That came
Newtonian,
largely from
yep.
Isaac Newton. And his way of thinking about the universe persisted, largely intact, for hundreds of years. But then Albert Einstein came along, and he had a new thought that caused our entire view of space and time to wobble. Oh, look how cool this is. But before I explain how did Einstein make our whole understanding of the universe wobble?
The important thing to remember is that scientists, especially physicists, are lazy people. That's the most important thing. And what I mean
I don't doubt that.
by that is that we want the minimal number of equations to explain the most stuff.
The holy grail here would be one equation or theory to describe everything. But we're not there yet. A few decades before
Theory
lazy
is
Einstein,
everything. No.
lazy James Clerk Maxwell had realized that he could distill all of electricity and magnetism down to a single thing described in just 4 equations: electromagnetism. And those equations found that light was an electromagnetic wave. And these waves come
And a
in
particle too. It's also a photon, but sure.
different energies across a spectrum. And
By the way, this is all radiation. This is another word for light-based radiation.
weirdly, all light had the same constant speed.
And I think you can guess what that speed is. It's the speed of light. So
That's a bit like saying it's shaped like itself.
here we have an enormous, profound implication that shocked everybody. That's insane. It's nothing has a constant speed. That makes no sense.
But it's not just some equations. We have tested this.
You can slow it down a bit by running it through water, which is actually where the blue glow comes from in nuclear reactors, because certain particles actually go faster than the speed of light in water. So you can kind of cheat and go faster than light in certain situations.
This is incredibly widely tested. These are facts we can experimentally confirm.
Everybody was confused by this, because up until then, to measure something's speed, you divided how far it goes in the time it took to get there. But if light is always going the same speed, no matter the distance or the time, then there's something wrong here.
Maybe there's something wrong with what we mean by distance and time, or if not wrong,
Yeah, it's curved.
maybe there's something relative.
This was Einstein's huge if true moment. He realized that if light is always the same speed, then distance and time have to be able to change. Going back to our original Newtonian description of gravity, this part was distance. But if distance isn't stable, what is gravity anymore? It was so beautiful, and now the whole thing is breaking down.
So it only breaks down in certain extreme situations. For all practical intents and purposes, I don't have any issue with calling it a force. To an engineer designing a reactor containment vessel, it's a force. It doesn't matter if it accelerates due to a force pulling it down, or if it's following its natural path through curved spacetime, and what it experiences as weight is the ground pushing up on it, preventing it from following its geodesic. Whether it's a force or just geometry, doesn't really matter at that point.
Hang with me here. I need a little break. Remember when I said they called this the vomit comet?
I did throw up. Didn't get that on camera. But
No, stay true to its name. I think that's part of the requirements.
I'm feeling much better. John, what did you just call what I just did? Tactical chunder. A tactical chunder. Just a tactical chunder.
Okay, back to my guy Einstein. So he goes back to the drawing board to reformulate not just gravity, but basically everything else. He spends the next decade struggling with this relative nature of space and time, and like Maxwell unified electricity and magnetism, Einstein finally emerges with a new model that unifies space and time. Space-time. In Einstein's new equations, space-time gets warped by stuff, like our sun, or Earth, or a black hole, or even
3 dimensions of space and 1 dimension of time.
you. In some infinitesimally small way, you're warping space and time around you.
I love that. Now, think about what that means.
Let's say I give you a little push, and you go floating off into space. If we zoom out and look at your path through space-time, we'd see that it's not actually flat. There's all of this stuff warping space-time around you. So you're going with the flow. And the main bit of stuff near you is Earth. And look, as you follow your path, you're drifting toward its surface. It looks like you're experiencing gravity.
Well, you are. By the way, in certain applications, you do need to account for this, for things like GPS timing, accounting for things like time dilation from Earth's gravitational field, as well as reactor control systems, and also calculations of exotic particles such as muons when you accelerate them in particle accelerators. So it's still very real.
But crucially, there isn't any force pulling you in. It helps me to think about it this way.
You have 2 people at the equator and you tell them to walk north. They appear to come together.
But there's no actual force causing them to come together. It's just the simple fact that the
Geometry.
Earth is curved.
Yeah.
That's all gravity is. Don't think about it as a force, think about it as the geometry of space-time around stuff.
Though the end result is the same, and like I said, you could still use the Newtonian equations and be close enough as far as accuracy is concerned, unless you're dealing with stuff like high-energy physics.
Actually, this classic view of a flat, warped space-time is also wrong. This is all just a visualization, but I try to imagine it more like this. But hang on.
Just like the classical view of atomic structure is wrong, where it shows them orbiting nice and neat paths, where it's really just probability curves.
This is just semantics. Why does it matter how I describe gravity?
Like, Newton's theory says that gravity looks kind of like this, and Einstein's theory says it looks more like this, but same but different, right?
Why does it matter whether I think about gravity as a force that literally pulls things?
Technically, it doesn't matter what you think. I mean, I'm pretty sure thought police aren't a real thing.
Or as the curving of space-time?
I think that's a great question. The reason why it matters is because Newton's law, which describes this mass pulling and that mass pulling as you described, it's not exactly correct.
Einstein's space-time leads to genuinely different predictions than Newton's forces.
And again, the answer is when dealing with relativistic particles or extreme physics scenario.
Thought about gravity like Newton, we wouldn't have accurate satellites or planes or Uber.
If you're calling Uber or
GPS.
Lyft and you're on a street corner, you would be off by kilometers. If you did not correct for the relativistic differences between where the satellite is that's receiving and sending the signals and your location down on the Earth.
How I think about it is, I don't think Einstein straight up proved Newton wrong. I think of it more as he extended it to more extreme scenarios that Newton didn't need to worry about. I mean, Newton didn't have Uber. And calling gravity fake is a bit like saying centrifugal force is fake. I mean, yeah, centrifugal force isn't really a fundamental force, but it's still going to smash you up against the wall if you're not braced for impact.
So it has an impact in our daily lives.
Impact.
Now I'm back.
There you go. That's I like her explanation.
Your face whenever you land is brilliant.
After everything that we've learned, what is it that I'm feeling right now?
Well, Einstein would say that you're just on a space-time path. Imagine for a second that the Earth isn't there, but somehow the distortion in space-time is. So you keep moving along your curved path. You're experiencing the same phenomenon as me floating in the plane. Gravity has disappeared. We're back to 0G. It turns out the only reason we ever feel gravity is when something stops us in our space-time paths. So if the only thing that makes you feel gravity right now is Earth stopping you, wouldn't that mean that gravity is sort of fictitious or fake?
In the same example about centrifugal force. I mean, I don't have a problem with the statement of saying it's not a fundamental force like electromagnetism, and it's an emergent property of space-time geometry. Sure. But it is indeed very real.
Is gravity a fictitious force?
Bingo. That's the part. That's what you've got it. This is why gravity was never there to start with. It's fictitious in that sense.
Yeah, gravity is a lie.
I would still be careful with that, especially the way people are throwing around the word fake.
In that case, I buy it. I'm with you. Except, if gravity is a fictitious force, how do you explain what's happening in empty space between the sun and the Earth?
Geometry.
Now, we're at level 3. If the goal for physicists
Gravity
is to
is not
use
like
as
anything
few
else.
equations as possible to explain the most amount of stuff, they've done a really good job boiling things down.
If you go back to your textbook and you talk about forces in the universe, and the picture used to be really complicated, there's this force, there's that force. But what we really know is you can boil everything down to 4.
The first two mostly just operate within atomic nuclei. The third
This is a different order than I'm used to seeing it as, putting weak above strong. But weak, mainly think of the force behind radioactive decay, or the conversion of a quark into different types of quarks. And strong is what makes nuclear power plants so amazing, because that is the force that holds nuclei together. And that is all the energy that is released from fission when you produce nuclear power. And number 3 is what you ultimately use number 2 for, to make electricity, and describes the phenomena of interaction with anything with charge. And I'm used to seeing gravity as number 4.
third is the force from charges attracting or repelling each other. And together, they make up almost every force that you experience in your daily life. And scientists
4 is question mark, question mark, question mark, so 5 is profit.
now agree that all 3 of these actually fit together.
Physicists have been able to basically write those forces in the same sort of mathematical language. It's the language of quantum mechanics.
Sure.
Quantum mechanics is awesome.
And why gravity is not there is because quantum mechanics is discrete, probabilistic, compared to general relativity being more smooth, that is to say not discrete values, and deterministic, rather than, I wonder what are the odds that I'm going to interact gravitationally with this object. That's not really a thing.
It is our most accurate and successful model of the universe ever. It describes our universe as chunky.
I think the reason why it's so accurate is because it's all based on probabilistic math. Just like we use probabilistic math to determine the odds of neutrons interacting with certain particles, such as boron in a control rod versus causing fission in a uranium nuclei. We also use probabilistic to do risk-informed decision-making. Say whether you take down a safety system for maintenance, how that's going to affect the odds of an accident resulting in core damage, or meltdown, as the media likes to call it.
With these tiny, discrete, or quantized particles. But it still can't describe what's happening here. Because which force
They don't play well together, general relativity and quantum mechanics.
is at work here? It's empty space. It's none of these 3. So physicists had no choice but to describe what's happening here as a 4th force.
Like the nuclear strong force, for instance, is modeled great using quantum field theory. But gravity resists it. Gravitons aren't really a thing.
Uh-oh. Here comes gravity.
We've just had this long conversation about how gravity isn't really a force. And now what you've done is you've stumbled into the biggest problem of 20th century and now 21st century physics.
Hang with me here. We are getting
Couldn't find it out by the end of the 20th.
right to
did
the
we?
cutting edge.
But there's a really big problem because
Got a
these
few?
two,
No.
they predict different stuff.
They are in conflict. Gravity would make predictions that say quantum mechanics is wrong. Quantum mechanics would make predictions that says, relativity is wrong.
And that sucks because if we could just
The following statement is true, the previous statement is false.
combine the two, we could do so much more. So why can't we just do that?
What is the problem? I mean, why can't I write gravity in the same way? Because unlike the other forces, I can make gravity disappear, right?
In the plane.
Yeah, in the plane, gravity disappears. With the other forces,
you don't lose
can't
charge.
make them disappear.
You don't lose the strong nuclear force, thankfully. You would have all kinds of problems if that happened.
Part of the reason we can't unite them is, do you remember those quantized particles in quantum mechanics? Gravity doesn't seem to have one. We can't find any chunks of gravity.
So our situation right now is this.
We have one set of math for the little stuff, or the quantized particles, and we have another set of math for big stuff that's smooth or continuous. But the holy grail for physicists is trying to combine these two. This is
It tried with string theory, but no.
the theory of everything. We're now at level 4. Okay, here are the options that the smartest people on Earth have come up with for the theory of everything, explained in simple
gonna be
terms.
string, isn't it?
Option 1. You basically shove gravity into quantum mechanics. That would probably require finding that missing particle
Force it in and see what happens. All right.
for gravity, a graviton. But unfortunately,
It doesn't work. The mathematics does not work.
for one thing, even if you did find a particle, how would a particle just disappear like gravity does? So most scientists are exploring option 2. You stick them together.
The mathematics that people are trying has become really quite complicated to stick these things together.
There are a bunch of ways to try to stick these things together, and you might have heard their names over the years. This is string theory, M theory, loop quantum gravity.
Ooh, that
The
one's a fun
most
one.
important one to know
Chunks of space-time. I like that one.
about is this paper. This is the most cited paper in all of theoretical physics.
yeah.
The author seems to have found a thread of a connection between the tiny quantum stuff and the big continuous gravity stuff. And it's the first time that we've made this connection. But it is so complicated that I couldn't understand it by reading the paper. So I just called him up.
The objective
Oh,
I
there
had
you
when
go.
writing the paper was to understand gravity.
What he came up with is at the edge of theoretical physics. If you started this video at level 1 and you end just knowing the name of this theory, that's awesome. It's called ADS-CFT, and
sure.
the concept is in the name. This part describes the big, continuous gravitational forces in our
For
universe.
space-time, yep.
And this part describes the small, chunky, quantized forces. But what's really
C stands
exciting
for
to
chunky.
physicists
Not
is,
really.
weirdly, this slash in the middle. Because what this slash represents is the fact that the two ideas are actually connected here mathematically.
It looks like gravity has something to do with the entanglement or correlations that exist in the system of particles that we are discussing.
Trying to model quantum gravity using tools from quantum mechanics, if you can.
This theory describes a thread that might connect the two, but it is very complex
be
and
confused
makes
with
some
string.
simplifying assumptions
Yeah.
and has parts of it that are still unsolved. But it
I've heard the explanation for, some of it you get into the whole spherical chicken territory. Kind of like the whole ignore air resistance argument where you have to, things only work in certain situations.
it's a glimpse of what might become a theory of everything.
Yeah, but we don't yet understand it, but if we understand it, we'll be able to explain more aspects of the universe.
And this is where I just start to dream big. Because if we can fully
we go.
understand gravity, who knows what we could build? I'm imagining flying cars and close to light speed travel
Anti-gravity.
and hoverboards and
Anti-gravity, faster than light. That's jumping the gun a bit much, but I guess it could start out leading to tools, assuming this actually works out, that could simulate the quantum effects of gravity. Could help with fusion confinement or reactor shielding in really high energy environments, which I would say would certainly be a requirement if you're going to build more powerful reactors that use something more exotic than, say, uranium or thorium.
I don't know. Maybe it's far-fetched to think that one day we could manipulate gravity. But if we never understand it, we never will.
So if you could control it, you could lower fuel costs in launch systems, help with asteroid mining or terraforming even. Though it's still going to use energy from somewhere, so what you're not paying in fuel costs for, say, getting a rocket into space would be for energy costs of your device that manipulates gravity. So you're still not getting something from nothing here. But there's no experimental evidence that we can even make or block gravity. It's a bit like trying to make a fusion reactor using anti-gravity containment. It's like, okay, but like you said, there's no graviton particle, there's no negative charge, there's no gravity charges like you have, so we're kind of stuck with electromagnetism there.
Physicists are trying to strengthen this thread to maybe one day be able to explain the entire universe.
That was incredible.
You flew so well, you're a natural.
I'm gonna remember this for the rest of my life. So we started with Newton, and then Einstein, and then quantum mechanics, and now the theory of everything. And with every step, we're getting just a little about. And yet, even with all of this incredible science, it feels like we're just at the beginning. Solving this big mystery won't be easy, and
yeah, a lot of things we kind of are.
It's not guaranteed.
This is a physicist's dream, and the universe doesn't have to play ball, right? We've had this feeling in our gut, oh yeah, the universe at heart must be beautiful.
Einstein might be open to another correction, just like Newton was.
Must be simple.
Maybe it's not. Maybe it's beyond our ability to understand. I hope not. After all, it wasn't so long ago that humans figured out planets and atoms and so much more. We can do this. And as you're watching this, thousands of scientists here and all around the world are working to better understand our universe so that we can all build what comes next.
I like that this was uplifting. Thanks so much for the recommendation, and thanks so much for watching. I'll see you next time.